pins up the videos of the panelists. So so our panelists today include Scott Aaronson, who again needs no introduction here. He was a speaker and a panelist before. Let me just give the update that as of his last appearance here, he won the ACM Prize for Computing. So congrats, Scott. We have Sergio Boixo, who's chief scientist at Google. I believe Sergio was one of the major players in this whole benchmarking for the quantum supremacy experiment at Google. So it's really great to have you here, Sergio. We have Steve Flammia, who until recently was at the University of Sydney and who is now at the AWS Center for Quantum Computing. Steve is an expert in quantum information, especially as applied to condensed matter theory and to error correction. And in fact, he's done a lot of work on learning, benchmarking errors in near-term quantum systems. So welcome, Steve. And then we have Joseph Emerson, who is on the faculty at the Institute for Quantum Computing and at the University of Waterloo. He's also the CEO and founder of Quantum Benchmark. So again, welcome, Joseph. And so I guess John gave just a. I mean, there's a lot to chew on from John's talk. There's plenty to address there, but I'd also like to broaden the topic out to quantum benchmarking, which is clearly something that's going to play a big role as we move ahead with quantum devices. I'm sorry. I hope John's video is also being pinned. Omid. When I was a student here at Berkeley, there was a architecture professor who said that the most important application of computers is designing better computers. It was probably true at that time in computer science, and maybe it's going to be true in quantum computation at this particular point in time. So anyway, I guess with respect to quantum benchmarking, of course, we want to learn what our current day quantum computers are, in terms of how well they're doing, how to improve them, how to understand the error models in there, and so. It would be great to hear your views about that too. So perhaps we can go through, one by one, if you can speak for a couple of minutes about any of these topics. So we start with Scott, since.
All right. Well, yeah. So I'm grateful to John for an exceptionally clear presentation of one of my favorite results of the last. Couple of years about, learning of quantum states. I mean, I have been interested for a very long time in this business of how can you predict many properties of a quantum state from few measurements of that state. Right? I mean, even before shadow tomography in 2006, I had this paper about pack learning of quantum states, right? Where, let's say I only need to predict a quantum state with respect to most measurements that are drawn from some distribution over measurements. And then, I showed that you could do that with a number of samples that grows only linearly with the number of qubits. And that was, that result was actually what part of what led me to formulate the question of, is shadow tomography possible or not? But, my suspicion was probably it's not possible, but this was one of those cases where you fail to prove something is impossible, and then ultimately you discover the barrier to the impossibility proof was that it is possible. So But, I've also, so I guess, for 15 years, I've talked to experimentalists about, and I've tried to interest them in these ideas of sort of quick and dirty quantum state tomography that could be, exponentially more efficient than the full kind. And, there's been a lot of curiosity about it, but, there've also been sort of, I think, some major barriers that have sort of prevented them from really, using it for anything practical, right? One difficulty has been just the complication of the measurements that you had to perform, in the sorts of protocols that I explored. John mentioned that in his talk, right? A second issue is, the computational difficulty, right? Just because you can do something with a number of measurements that's linear in the number of qubits doesn't mean that you can actually do the computation that efficiently, right? And that might still require exponential and n computation, okay? But I think maybe the biggest issue has been the lack of a sort of killer application, and what's happened again and again is that, like, once the experimentalists specify what thing they are interested in, then often, there is a more direct way. If you just wanted to learn that property of your state, or if you just wanted to learn all of the k-point correlation functions where k is small, then there would be some much more direct way to do that that wouldn't require, the strength of these abstract learning theorems, right? So, listening to John's talk, I had, I occasionally had that question in the back of my head, like, John, you talked about, like, learning, the ground state energy, right? Or learning the energy of a state. Like, if you just wanted to know the energy, then why not just sort of directly estimate that, right? But on the other hand, what I really like about this classical shadows idea is that there is sort of one thing that you can tell experimentalists to go out and measure, namely, the results of, like, applying a bunch of random unitaries from some ensemble, like random Clifford circuits, for example, and then just measuring in the computational basis over and over again. And from that, you can collect a whole bunch of classical data where, you don't even have to know in advance what that might be used for, right? You then have some classical archival record of this quantum state that could be then called upon later for something that you might not have even thought of at the time. And so I think that that's precisely what could have a lot of appeal to experimentalists. And yeah, I hope that more, applications will be discovered that really, sort of draw on this and use it and need it.
Great. Thanks, Scott. Sergio, with you.
Hi, sure. Yeah, so I guess you were posing the question, what are current experimental quantum computers good for and why it's important to keep benchmarking them? And I think, yeah, your answer is a pretty good one, to build better quantum computers, especially when we're thinking on the long-term plan of fault-tolerant quantum computation. Is, very difficult to have really advanced, precise enough models that tells us how we need to keep improving the system, making sure that we have all correlations under control. Lately, we're very worried about cosmic rays, for instance. There is a lot of work that we are going to have to do there to mitigate the effect of cosmic rays by removing energy from chips. So clearly, in the context of error correction, it's very important to keep doing experiments and improve our models to guide the design of new generations of superconducting qubits in particular. And I will guess the same applies to other systems. So it's important to do very detailed benchmarking to improve models and have a learning cycle to keep improving designs. But also I think for NISQ algorithms, is as well very important to do experimentation as we keep improving our algorithmic techniques. I think one particular point where experimentation is really important is general error mitigation techniques. There are many interesting error mitigation techniques out there, and it's hard to see a priori which one is going to work better or worse for a particular experiment. And on that note, for instance, one of the papers we have done recently at Google, one of the experiments was the information scrambling experiments, looking at autocorrelations And I think we found something interesting there, which is that once you apply all the error mitigation techniques we could think of, and we compare against the latest algorithms for simulating these kind of circuits. These were random circuits. It was information scrubbing random circuits. So when we compare with the classical cost of simulating the same circuits with the latest techniques, which is basically tensor networks with hyper-optimized contractions, the conclusion is that we need to lower our error rates by a factor of a half to be able to measure autoc observables in a regime that we cannot simulate classically anymore. So on the one hand, that's encouraging. It's just, a factor of 1/2. It's not a factor of 100. On the other hand, lowering error rates by a factor of a half is hard. And I guess the point I'm trying to make is that this particular estimate that we need to lower error rates by a factor of a half, that will be very hard to do without actually running experiments, because that includes a lot of error mitigation techniques. And it wasn't easy to see a priori which error mitigation techniques were going to work better. In this particular case, it turned out that some sort of error extrapolation where we kind of implement Clifford circuits, which were in the support of the random circuits that we care about. And because they're Clifford, we can measure everything exactly. Then we can get the constants to do proper error extrapolation. That particular technique worked well, but it's kind of an involved technique that, it wasn't a priori, I guess. Like I just try Clifford circuits on the support of the random circuit that you care about. So yeah, I think experimentation and benchmarking with actual devices is quite important.
Oh, great. Thanks, Sergio. Stephen? No.
Right. So I guess Scott and Sergio touched on this point, but since you asked us to discuss benchmarking more generally, is what I think you said. I think it's important that we distinguish two different notions of benchmarking that are used in the literature. So the first is what might be called error benchmarking, and the other is what might be called application benchmarking. So if you talk about error benchmarking, you're talking about estimating error rates, which Sergio alluded to. And if you're talking about application benchmarking, you're talking about how well is a specific quantum device going to perform at a specific task. And these are two separate things for which the community unfortunately uses the same word. So there's some confusion there. And I think that actually classical shadows is going to be useful for both of these regimes. I think that we can learn a lot from the type of randomized experiments that John talked about using estimation from classical shadow estimation. In fact, for one of the reasons that Scott talked about, which is namely that you can sort of collect this data in advance with these randomized experiments, and you don't even have to know what you're going to process it for. So you can, after the fact, decide to do things like model testing and model selection on the error benchmarking side to try to determine error rates. And you can also try to process that data to try to see, you're interested specifically in estimating an energy of some local Hamiltonian, for example, is an application of these classical shadow techniques. But you can also use that data, those same data can be used for estimating the usefulness for some other tasks, potentially. It depends on the structure of the circuits. But I believe that classical shadows will find applications like this in the future. So I'm excited. I think keeping these, so what Sergio also, another point that Sergio made is that error mitigation is important. I mean, error mitigation is like a jargon term that our field came up with because of a high impact paper that was published, but it's really just debiasing. Our community isn't the first to invent this notion that if you have biased estimators, you have to remove the bias on those estimators. We use error mitigation in this specific context. So I think all of these things are going to be extremely important. I think classical shadows are going to play an important role in all three of these things moving forward.
Sorry, thanks, Steve. Joseph.
Oh, thanks. Yeah, thank you for the presentation, John. And well, am I muted? Yeah, I'm not muted. Good. And thanks for the invitation to participate in the panel. Yeah, actually, I'd like to kind of riff off of what Steve was talking about. First of all, the terminology. I totally agree that benchmarking is kind of an overloaded term. I tend to use it to mean both of those things, unfortunately. But when I'm on my best behavior, it's benchmarking. The notion of benchmarking that we care about is really error diagnosis, error characterization. And I think we have kind of our human weakness to want to turn this into a competition and talk about benchmarks that can compare platforms. But I think ultimately it's really too early for that. We should be focused theoretically and academically and in industry on error diagnostics, and in particular error diagnostics that help us get to the killer app, which is quantum error correction. And so I try to use the word error diagnostic to mean we need a lot of information. It's easy for people to oversimplify the idea that getting to the fault tolerant regime is about proving you have this one benchmarking number that's below threshold. And really, noise is complex, and to understand the overheads involved and the most effective error correction strategy and decoding strategy, we need detailed information, detailed diagnostics about the errors. And I think that in terms of work that's going to move the field forward, I feel like that's the biggest priority, is to pull that information out and fold it into a process where we can start making positive, strong inferences, like Scott was saying about, you can just measure the certain number of measurements and predict a lot of properties of the state you might find out later. And, we need that process in place for error channels to understand, what are the details of the error channel, which will inform our decisions about how to ultimately not just, mitigate the errors, but correct them through an error correction layer. So, I'll just keep my comments brief and say, I think that's the biggest challenge in front of the field right now.
Great, thanks, Joseph. John, would you like to respond?
Well, I guess I'd like to ask a question to the panel. This was kind of addressed by Joseph and Steve, but our big challenge in the NISC era is noise mitigation. Joseph said, well, one of the reasons we want error diagnostics is to advance us on the path to fault tolerance. Steve spoke of the importance of reversing bias in estimators, but I would be interested in your perspective on how much headroom there is for noise mitigation in the NISC era. Do you think that it's possible to come up? I mean, a lot of people have offered various ideas for trying to get useful results out of noisy platforms. But do you think there's opportunities to make big advances there, which might make NISC technology much more useful?
Oh, Joe, do you want to go? I saw you unmute too.
I've been unmuted, so it's an indicator, but I'm happy to maybe I'll start a bit and you can follow up, Steve. I think there is a big opportunity, but we need to know more about the nature of the errors, the extent to which they're, I think calibration errors, we can make a lot of progress. I mean, ultimately there's limitations in finite control. One of the things I like to say, which, it took me a long time to kind of realize this is the right way to think about things, is, we talk about decoherence as the Achilles heel for quantum computing. But, the more work I've done with experimentalists, the more I realize that in a sense, depending on how you define that term, that's actually not the problem. The problem is calibration and control errors. We're using, finite precision analog signals to get, some kind of continuous rotations in Hilbert space. And there's always going to be a finite precision limitation. And these coherent errors can have very negative effects. First of all, they're ubiquitous and they can be very problematic. They don't fit our simplest kind of theoretical models. And so, I think there is a lot of promise to mitigate those errors through, control strategies, informed control strategies in particular. Whereas I think, problems of decoherence where it's straight up coupling to an environment that's outside of our control, I think that's really up to the fab process, which is outside of my wheelhouse. And there, I can't really speak to what can be done at that level. Steve, do you want to take it from there?
Yeah. So John, you asked, how much room is there for progress on noise mitigation in near-term quantum devices. I think there is room for a lot of progress. I think a lot of the techniques are going to have bad scaling, possibly exponential scaling, although there have been some papers that have a promising scaling. And I don't think that that's necessarily a bad thing. If you throw some mild exponential scaling of classical resources, it's something to unlock a better scaling from your quantum resources. That's great. And if you manage to actually do something useful, wow, that would be fantastic, right? That's what we're all hoping we can achieve. What we'll really get out of all of this is, going back to what Umesh said, we'll learn how to build better quantum computers from doing this. So I think that there's going to be huge payoffs from the investment that we make in these ideas. Do I believe that we're actually going to be able to use noise mitigation techniques to do a useful quantum computation that can't be done, let's say, easily classically, or maybe not done at all on a huge cloud computer? I wouldn't put great odds on it. I'm not super optimistic, but hopefully I'm wrong. But I do think that it's going to unlock a lot of power in future devices where we do have error correction and fault tolerance.
If I can jump in again, I might be speaking to the wrong topic. So I've been using the term error mitigation to really mean kind of any method that's going to suppress the native hardware errors, whether it's anything from decoupling pi pulses to compiling strategies, to the methods that were proposed around extrapolating performance based on some assumptions about the
I was mainly talking about extrapolation rather than things like dynamical decoupling sequences. But
okay, so
anything is fair game to reduce noise. But once you have the data, trying to remove that noise post facto, that I think is challenging. Generally, often has bad scaling. And it's not clear to me that we're going to get a quantum advantage by using those techniques. I think without those techniques, things are even worse off. So we should be using those techniques. And like I said, the investments that we put into developing those techniques are only going to help us build actual quantum computers, which is going to, by which I mean fault tolerant, error corrected quantum computers. So I'm all in for these ideas. I think they're great. I'm not super optimistic that we're actually going to get a quantum advantage from those techniques if they don't come in tandem with other improvements elsewhere. So,
yeah. So if in the narrower context of that type of error mitigation, I'd have to say I'm a bit skeptical about how effective it will be in a context where we can't verify that the extrapolated solution is correct by independent means. I'd be worried about that.
Shall I try to address the question a little bit?
Yeah.
I think the main problem from error mitigation is that it's not removing errors, and fidelity is, of course, decreasing exponentially with the number of gates, right? So, if you want to do more than 50 qubits and that 50, well, then you're likely to have pretty low fidelity. Maybe you can get to 100 qubits, that's 100. But fidelity keeps decreasing exponentially. The current techniques in error mitigation, which is not error correction, they're gonna scale as 1 over fidelity square or 1 over fidelity. So I think that the current techniques that I know of are actually 1 over fidelity square. And they, of course you want to remove fault control errors and calibration errors first if you can, but then you're still gonna be left with, an NT1, NT2, things like that, which is coupling to an environment. You cannot remove that. Current error mitigation techniques are limited. They have a cost, which was like 1 over fidelity square. So that, limits the application of error mitigation, which is not error correction. I think what will be great is to find error mitigation technique like error detection with a cost that will go like 1 over F. And that's probably the best we can achieve in what I'm calling error mitigation. that means sort of actually removing errors. So I think the best you can do is hope for a technique which allows you to flag errors, and then you just post-process, remove all the data with errors out of your sampling. And assuming that you can do that without introducing any overhead in the shortcuts, then the best you can hope for is that the cost of the optimal irrigation will be 1/f. But as fidelity keeps decreasing exponentially, this is still limited. And the other thing I would like to say is that I think, more optimistic about finding, beyond classical applications or quantum advanced applications in the NISQ era in some specific areas. For instance, I mentioned AUTOC, or information scrambling, which is, looking at correlators of operators or really random circuits. And we're only a factor of a half away from that. I think probably for, spin diffusion or Boixo models, we're probably eventually going to get beyond classical simulations on NISQ. I'm more, pessimistic about fermionic simulations, at least with superconducting qubits, because of all the overhead. But in some areas, which, versions of random circuits and maybe spin diffusion, I think we're likely to, get somewhere in NISQ.
Great. Maybe shall we see if the audience has any questions?
There are some questions in the chat and the Q&A.
Yes, so
Not sure if you can see them.
So there is a question by Peter M in the chat. Can anyone comment on the claim by PsiQuantum where they say they'll have 1 million error correcting photonic qubits? I'm not sure who wants to take this question.
I'm sure we all hope it's true.
I think John should comment on that.
It's good to have ambitious goals.
okay. Anyone else?
Maybe I can ask a question if you'd like.
Yeah, please.
John, sorry for my negative tone of question earlier. I really do like classical shadows a great deal, and I'm happy the panel is discussing noise, because I have this fundamental belief that no algorithm is real unless it survives finite amount of noise. And so I'd like to push and see how far it can go. But one direction that occurred to me during your discussion might be to ask, do you, the panel, believe that we could turn this around and utilize shadow tomography or classical shadows to study noise and use it as a technique to understand noise processes? Because as you said, John, if it's like independent noise, it may not affect it. If it's biased noise, it will affect it. If it's highly correlated noise, it will probably affect it more. Many quantum noise sources are highly correlated. I wonder, what do you think?
Well, I defer to Steve and Joseph as the experts on noise characterization.
I think the answer is yes. I think that this can be done. I have a few thoughts about it even, but they're probably not ready for. They're not. They're still quarter baked or maybe half baked. So maybe in the future we can talk about that more. But I think it should be possible.
While we are waiting for anybody else to ask questions, let me ask a question, John. So do you have a sort of a heuristic way of thinking about this in terms of what are those tasks, or where classical shadows where the efficiency in terms of computation or samples, what's that set of tasks where this is going to be efficient?
This is for me, right?
Yeah.
Well, I don't know. I gave some examples,
Sure.
and they're probably the best examples I could offer. But I think we can benefit from kind of thinking broadly about it. That you know, because I think it's a key question for the near term. So we're going to have quantum platforms, and we'll be able to prepare certain kinds of states, and then we want to use them to do something useful. And we don't want to rely on relatively high depth quantum circuits. And so if we have the tool to take that quantum state and translate it into a succinct classical description that's useful for things, then, in searching for applications, I would suggest thinking about, what are the applications which can run if we have classical shadows as inputs. And that was what I tried to illustrate with the machine learning examples.
Yeah.
That, we have all this wonderful machinery for classical machine learning. And if we have quantum platform, which can prepare states which are not so easy to prepare classically, of course, maybe that's a big if for the near term, then we have the opportunity to, use the power of that quantum data to extend the reach of machine learning tools. So I think there's a lot of territory to explore there.
Actually, I have a follow-up question, if I may, for Scott and John. Yeah, so I mean, I still don't feel like I have a good intuition about how this is even possible, that such a small number of measurements can be so predictive so broadly. Could you maybe help me build up intuition by maybe giving me an example of something where it wouldn't work, so I can kind of understand the complexity that's lost? I mean, are there use cases where this would be insufficient? Like, one thing that came to mind is when it came to estimating the Hilbert-Schmidt inner product, which would be relevant for fidelity estimation, then you needed the full Clifford rather than the tensor product Cliffords, right? So that's a quantum resource, but it's still the same small number of measurements. So it's more than small number of measurements that surprises me. I don't know. It's an open-ended question. If any of you have any thoughts on that.
Well, I mean, in the case of John's protocol, if the shadow norm is large, then it's going to require a lot of samples, right? I mean, that's the thing that controls its efficiency, right? My protocol is sort of harder to implement, but it's more general, right? And that it would work for any list of 2 outcome measurements, like any collection of quantum circuits that you wanted. And maybe this will help your intuition a little. I mean, my procedure, if you wanted to learn the outcomes of exponentially many different measurements, then, although my procedure only needs a polynomial number of quantum of copies of the state, it will run for an exponential amount of time. Okay, it will make a measurement, and it will make measurements basically for each measurement in your list that you want, right? And just do it in a very gentle way that only rarely disturbs the states by much. Okay, but so it's a very inefficient procedure. The only thing that we're optimizing is, the sample complexity, like the number of copies of the state, right? And so that's part of what makes it possible. But of course, there's then an enormous space to explore in terms of, well, in what situations can you also make this computationally efficient? Just like with classical machine learning, first people proved, results about sample complexity, saying, well, like in principle, here is, like what you could aim for. And then people spent decades after that trying to fill in the gap with what actual procedures can we find for learning that will also be efficient computationally.
I guess a simple example would be learning a lot of highway poly operators. And I discussed that in the context of the poly measurement protocol, that it was you need an exponential number of samples in the weight. But even for the Clifford protocol, I mean, the Hilbert-Schmidt norm is exponential. If you just take the trace of, you're taking the trace of the identity for n qubits when you square the Pauli operator. So we can't infer that we can predict lots of high weight Pauli operators.
And maybe I can add something, some intuition for why you might expect a log M scaling with these things. So imagine you're trying to do parameter estimation, and often people are interested in the few parameter case or the one parameter case, and they are interested in achieving like an optimal constant given by a Fisher information or something like this. But you just want to get maybe not the optimal scaling, but like good enough precision. But you have a large list of parameters, you have M of them. And you take data that is somehow generic in that it's informative a little bit, but not optimally, about all the parameters. And that's what the shadows do. You can just recycle your data and apply it to each of the parameters on the list. And you're like, whoa, but that introduces huge dependencies. And like, isn't that a major problem? And you would think that it would be. But if the failure probability of each one is small, then you can take the union, it's decaying exponentially with all these protocols. You take the union bound over all of them. And then you're done. You just need a log M factor to compensate for, like a statistician would call it, multiple hypothesis testing correction, but I would call it the union bound. And this is what gives you the log M scaling. So, when you're trying to estimate all these parameters, you can do it in bulk and you can recycle your original data to do it. It's not going to always work. There are, some caveats that come with that, but like it's an achievable goal in a lot of circumstances. So you can aim for that, and you're not being unrealistic with that expectation, at least not a priori.
Thank you, Steve. I should add that Steve is actually the one who coined the term shadows in this context, right? When I had some stupid name for this idea, and Steve was like, "Well, why don't you call it shadow tomography?" And like, physicists are really much better at naming things.
Yeah, I agree. That's a great name. Steve, is it from Plato's Cave, the allegory of Plato's Cave?
Yeah. Also, like maybe it's worth, since I'm in a very public forum right now, to explain my idea. These aren't quite projections because the things that you're measuring don't commute. So rather than calling them just projections of the quantum state, there's some kind of shadow, which I thought, Plato's Cave, and of course I was thinking about Plato.
But I should say, in my shadow tomography paper, I did have this observation that Steve mentioned, that in the classical case, so the case where all of the shadows do commute, there the proof of the shadow tomography theorem is just 3 lines. It's just the Chernoff bound and the union bound. And that's where that log of M factor comes from, end of story, right? The whole difficulty in the quantum case is just that measurements on quantum states can destroy the state. And so now you have to be more careful.
That was super helpful. Thanks, guys.
Oh, great.
I'd like to sharpen Umesh's question if there's a moment to do so.
Please, go ahead.
So, Umesh, you asked the panel if there's something useful that could come out of this. And it occurred to me listening to you just now, why not create the density matrix and the states that you want from a natural physical system that already exists, such as a Bose-Einstein condensate that's evolving in a lattice that might be doing some Bose-Hubbard model or Fermi-Hubbard model. Why not look at a black hole astrophysically and then do classical shadow tomography with astrophysical measurements? Do you believe in this?
Am I supposed to answer this? So you're not trying to characterize the quantum state of the black hole. You're just talking about a protocol for using projections to predict what exactly?
I'm not sure. The astrophysical questions I'm leaving open, but clearly in the Bose-Einstein condensate example, there's a natural physical system that can be very complex, and it's quantum, and it may be accessible experimentally to doing the shadows that you describe.
Okay, well, that's like a kind of classical signal processing problem, I guess, that you're talking about, which you probably know more about than I do.
The way I understood it, he's replacing a quantum computer with a NISQ device quantum computer, which has gates, with an analog quantum computer, AKA an experiment. But as long as you can access the measurements at the output, I think you could use it still.
And so maybe classical shadow tomography becomes a useful tool of quantum experimentalists. And what I did have in mind is exactly what you described, Steve.
Yeah, I mean, I like to think of it also as a quantum fingerprint, but that name is already taken, quantum fingerprinting. You know, it's a succinct description that lets you reconstruct a lot of interesting information from a system. And it's easy to make these measurements. So people should do this.
Great. So maybe shall we wrap up here? So this was thanks everybody for a terrific panel, and thanks again, John, for a wonderful talk. That was really quite a treat. So next week we'll have Henry Yun speak about a proof approach to a proof view of MIP star equal to RE. And the week after, we have Ronald DeWolf speaking about quantum algorithms for optimization. So if you'd like to continue to the discussion, we have a Gather Town link in the chat. So please join us there. See you all next week. Thanks, everybody.